Hello, Chem students. Today we're going to talk about the concept of solubility. Our objectives for this video are to compare factors that affect solubility of gases and solids, and also to talk about what happens as far as the rate that they dissolve in water, and even to some degree how much dissolves in water. So, in the last video, we talked about water being a universal solvent. Normally, if we were in a classroom, I would ask, why is the water known as a universal solvent? If you thought to yourself that water is a universal solvent because it is polar, and a lot of things found in nature have charges to them, so therefore they're going to be attracted to one another, you would be right. So what is solubility? This video is all about solubility. What is solubility? Solubility is a value that is the maximum amount of solute that can be dissolved into a solvent. The maximum amount of solute that can be dissolved into a solvent. Some things that affect the rate or the speed at which it dissolves would be nature, like for instance, like dissolves like. Things that are very similar to one another, the more like they are, the more quickly they're going to dissolve. If you increase the temperature, you're going to increase the speed of a dissolving process. If you stir it or agitate it, you're going to increase the rate of the dissolving process. If you crush the particles, make them tinier and tinier, you're going to increase the rate at which they dissolve. And then finally, if your system is gases, then increasing the pressure is going to increase the rate at which they dissolve. Only for gases, not for solids or liquids. So, what's going on during a dissolving process? Well, as we said in the previous video, dissolving is nothing more than a tug-of-war between molecules. You have two opposing forces. You have the attraction between the solute molecules, and you have the attraction between the solute molecule and the solvent. If the attraction between the solute molecule and the solvent, the water, is greater than the attraction between the individual solute molecules, then the material is going to dissolve. If the attraction is greater between the solute molecules than they are to the solvent molecules, then the dissolving is not going to happen. Water dissolves each substance differently because the four different forces are different, so you're going to have different rates and different speeds and different amounts of being dissolved, because you are literally looking at the comparison of the attractions between the water molecules and the substance. So there's three major degrees of saturation. On the low end is unsaturated, which means I have not reached solubility yet, the solubility value yet. I haven't reached the maximum solubility, so I am less than the maximum. That is going to be an unsaturated solution. When you mix that together, there's going to be no solid dissolved, and actually you could put some more in if you wanted to. Second thing is saturated. Saturated solutions hold the maximum amount. So you put it in, and there may be a little bit of undissolved solid remaining in the flask because the liquid is saturated. It's maxed out. It's filled as much as possible. The water is grabbing onto as many of the particles as it can. And then the last one is kind of unique. It's called supersaturated. This is an example of, I think this is ammonium nitrate, whereas you can take some ammonium nitrate and you heat it up to make more and more dissolve, and then slowly cool it down. Slowly cool it down. And when you do, it will be this clear colorless solution. So you've actually managed to put more into solution than should be there. More solute is dissolved into the solvent than should. And then what they're showing here is this crucible tongue is dropping a small speck of the ammonium nitrate into the solution, and then suddenly you start getting all these spiky crystals as the crystals, the solids, say, great, now I have a place that I can adhere to. I can now leave solution because I didn't want to be in solution anyway. In a supersaturated solution, which is the one on the left-hand side, the solvent is actually holding more than it normally is possible because it's been heated and then cooled down. Once you add the seed crystal, it will recrystallize and some will come out, and then what will ultimately occur is this thing on the right hand side. When you're done, since you have some in the material, some of the material in the liquid, some of the solid, you're at a saturated solution over here on the right hand side. Okay, solubility. So many solids and gases dissolve in water. You know, we talk about anything ionic, anything that has charge, anything that has charged sides can dissolve in water. So for instance, when you have Coca-Cola or any cola drink, you've got sugar in there, you've got carbon dioxide in there, you've got flavor in there, you got all these things dissolved in the water. As you increase the temperature, you can dissolve more solid. So as you increase the temperature, the more and more solid will dissolve into the water. That's one of the reasons why for the supersaturated solution, you heat it up to get more to go in and then kind of trick it into hanging onto it for a while by slowly reducing the temperature. But with gases, that's different, and you know that. If you've ever had a soda and it's gotten warm, what happens? Well, the bubbles come out, the fizz comes out. So for gases, when you increase the temperature, you're increasing the kinetic energy of the gas molecules, which means they're more apt to leave the solution. So they have more energy, so they want to leave the solution. For solids, it's the other way around. The more liquid there is, the more movement there is, more they're banging into the solids and making that dissolving more aggressive. So it's not the same. The kinetic energy goes up for gases, and when they have more kinetic energy, more comes out of solution. So you have more of a fizz. It's actually another reason why, if you think in terms of solubility, that classic Mentos experiment, what you're doing is taking sugar and putting it into a solution that has a whole lot of bubbles. It's the reason why you choose Diet Coke. Diet Coke does not have sugar in it. But you put a Mentos in there and it very quickly dissolves in the water and then needs to displace all that carbon dioxide that's in the solution, and boom, you get that big massive explosion of the gas bubbles escaping from the Diet Coke bottle. So this is an example of a solubility curve. Let's read into this. On the left hand, or the y-axis, you have the amount of solute in grams that will dissolve in 100 grams of water. I'll say that again. It's the amount of the material that will dissolve in 100 grams of water. So if I were to look at this and read this graph, I would see at 0 degrees Celsius, which is right near freezing, I could have 90 grams of ammonium nitrate, of ammonia dissolving into water. Okay? But I could have, say, 127 grams of potassium iodide. So these intersections all represent the amount of solid, amount of material that can dissolve in 100 grams of water. And then you see the temperature. As you go from left to right, it goes through the entire spectrum of when water is a liquid, from 0 degrees where it starts to be a liquid to 100 degrees where it starts to boil. So, which compounds are gases, and how do you know? If you said that HCl, NH3, and SO2 are gases, you're right, because you'll notice as it heats up, their solubility, the amount that can be dissolved in water, decreases, whereas everything else either stays really close to the same with sodium chloride, or it increases as you go across. Let's talk about how you read this chart. So here's the chart, another version of the chart that has less on it, but has another version chart. Question might be along the lines of how much KCl can dissolve in 100 grams of water at 50 degrees. So we're going to read our graph. We're going to find our 50 degrees and move up to the KCl. And then we're going to look over to the solubility graph and realize that that line intersects somewhere near the 42 grams. So what that tells me is 42 grams of potassium chloride can dissolve in 100 grams of water. That's very important, the 100 grams of water part. If I had 200 grams of water, I could dissolve twice as much, or 84 grams. Let's try another one, a little more weird. So suppose I want to dissolve 100 grams of sodium nitrate. I want to dissolve 100 grams of sodium nitrate at 20 degrees Celsius. 100 grams of sodium nitrate at 20 degrees Celsius. How much water do I need? Well, first I got to figure out, how much, what's my ratio at 20 degrees? So for 20 degrees, I can go up here and I can see that about 89 grams of sodium nitrate can dissolve in 100 grams of water. Okay, 98 grams of sodium nitrate can dissolve in 100 grams of water. But that's my conversion factor. I want to dissolve not 89 grams, I want to dissolve 100 grams. So 100 grams at a ratio of 89 grams of sodium nitrate per 100 grams of water, cross out my grams of sodium nitrate, I find that I would need 112 grams of water to dissolve my 100 grams of sodium nitrate. This table in each one of the intersections represents a ratio between number of temperature, specific to temperature, and the number of grams of the solute that can dissolve in 100 grams of water. Grams of solute that can dissolve in 100 grams of water. Let's try this one. How much potassium nitrate will dissolve in 1.5 kilograms of water at 40 degrees? How much potassium nitrate will dissolve in 1.5 kilograms of water at 40 degrees? Well, first we read the chart. 40 degrees, got the potassium nitrate. I see that I have about, what is that, at 62, 63 grams of potassium nitrate can dissolve in 100 grams of water. 63. So if I have 1.5 kilograms, which is the same as 1,500 grams of water, and I know that 63 grams of potassium nitrate can dissolve in 100 grams of water, again, grams of water will cancel, I could dissolve as much as 945 grams of potassium nitrate in that 1.5 kilograms of water. Okay, so the main reason why this is thrown into this chapter about the water and all its classifications and dealing with the bay is the concentration of dissolved oxygen and other dissolved minerals which are necessary for the bay's health is dependent on all these factors. So when we have pollution in the water, we have a situation where there's less room for those good nutrients to be dissolved. When we have murky, mucky water, brackish, not necessarily brackish water, but very cloudy water, we have less place for the good nutrients to be in the water. When the water is warm, the oxygen is less concentrated in the water. So our bay is very, very dependent. Our Chesapeake Bay is very, very dependent on a lot of solubility factors because for the wildlife to survive in the water, we have to have adequate minerals, nutrients, and oxygen in the water. And when other things are in there besides that, that's not going to be healthy. Okay, so that's the lesson on solubility. Hopefully, as everybody continues to stay healthy, safe, and practice your social distancing, I will see you on the next one. Toodles.